Can people read this? Size-wise? If I make it a little... Can people read this at the back? Yes? No?
I think they're saying
no. No? Thumbs down if you're no. No. Okay.
We'll just go with this for now.
Yeah. Okay, welcome to Lecture 5. Let's get started. I want to pick up today with where we left off last time and talk about one more proof, just so that we get the hang of, doing proofs together. And the real trick about proofs is that there is none. You just have to practice. And the more you practice, the more you play with things, the more you try out ideas, and the more types of proofs you see, the easier things will get. I want to acknowledge up front that proving things is hard. We don't expect you to be able to do complex proofs the first time you see them. A lot of this is something that, people get better at over time. And, people can take classes well into their PhD and even beyond on different kinds of proof techniques and how to prove things. And it's something that you shouldn't feel bad about if you don't get on the first try. It's something that you'll get better with over time. So before we start lecture, there's a few small announcements. First, we just posted to Piazza about this, but as you might have noticed, some of the discussion sections are quite crowded, and some of you might not be getting seats in discussion section. There's a bunch of sections that are actually undersubscribed, so there are open seats in these discussions. So if you would like to have more personal attention in your discussion sections, we posted to Piazza sections that, don't have a lot of students coming. So maybe try to attend one of those so that you can, get more interaction with the TAs. We also wanted to remind everyone that we do have the one extended section where we cover the same material, but go a little bit slower. So if you think that might be helpful to you, feel free to try that out. Finally, the last thing I wanted to remind people is that I know that there's some folks that, the homework is long, it's hard, and sometimes you make a mistake on the homework or, things go wrong. And for this, we basically have homework recap office hours. So there are 2 office hours on Monday where we will discuss in a discussion style setting the solutions to the homework that you just submitted. So in case you want to try and resubmit your homework, or you want to, make sure you're doing your self-grades right, or you just want to, have another pass at the homework, please go to those. They're a great resource where a TA will basically walk you step by step through the homework. They're 2 times at Monday, I think 9 a.m. and I don't want to say the times because I might get them wrong. I think it's 11 a.m., but I'm not 100% confident. So please check Piazza. And if you feel like you want to just get your self-grades done with a group of people, do them fast, or you want to resubmit your homework because maybe you messed something up and you want to make sure you're understanding it, I think this is a great resource that you can use to try and, learn the material better. Okay, so with that, let's start today's lecture. I'm going to do one more proof. And then I'm going to talk about linear transformations. And finally move to matrix multiplication. By the way, please, I ask you that if you cannot see stuff at the back of the room, please tell me. I have no idea of knowing what it looks like from back there, so if you can't see it, wave and let me know that you can't see. Okay. So there were a bunch of questions that I got last time on what does without loss of generality mean? Sometimes we abbreviate this as WLOG, log. And without loss of generality basically means that let us consider a specific case, but by choosing this specific case, we will not be losing any of the essence of the more general problem. So you can usually do without loss of generality. You can say without loss of generality when labels and reordering really doesn't matter. And so in the proof last time, we said without loss of generality, let A1 let's see if I have this. We said without loss of generality, let A1 be that column that is a linear combination of the other two. Right? We know from the definition that one of the columns is a linear combination of the other two, but we don't know which one, right? So we're saying, let's choose it to be A1. It might be the other one, but the proof structure will go through exactly the same. And so, as an example, let's say that, you have 3 numbers, A, B, and C. You can say, without loss of generality, let A be the largest number. You can also say, let C be the smallest number. You see how, in this case, when I'm given 3 numbers, it really doesn't matter which one I call the largest or the smallest because I don't know anything about them anyway. It doesn't matter which number I call what. So if all I have is just 3 numbers and I know nothing else about them, I can easily relabel them, right? Or without loss of generality, if I'm given 10 numbers, I can say let A1 be bigger than A2, be bigger than A3, so on and so forth. I'm not imposing any properties. Yes, question? In the more complex case where it's not so obvious, do you have to prove that it's without loss of generality? In some very complex situations, you might have to, but in general, you will only use without loss of generality in situations where it is obvious. Other cases, you would then, if it's something that requires a proof, you would not say without loss of generality. You would say, let us assume some property about variable A, and then say, prove that it doesn't matter that you're assuming that. So if it's not obvious, you wouldn't use the term. But basically, you will use it largely in this context of relabeling and reordering. That's mostly when these kinds of things will come up. Okay. So that's what I wanted to talk about, and we're going to get the chance to use this again in the example that I want to do. So we proved a theorem last time, and the theorem we proved last time was that if the columns of A are linearly dependent, then AX equal to B does not have a unique solution, right? There was an if here and a then there. But the natural question is, and I think some of you were asking that, well, what can we say about the columns if we know something about the equation? Right? This is saying if we know something about the matrix, we can say something about the number of solutions. Can we go in the other direction? And so the theorem that we want to prove today is theorem if AX equal to B has 2 or more solutions, then the columns of A are linearly dependent. So this is a theorem we want to prove. And now that you've all had some experience, trying to play with proofs, take a couple of minutes to try it out with your neighbor. Think about it on your own. Follow the steps that we talked about last time, right? I can put them up so that you can be reminded. So how are people doing? Do people have some idea? Do you want a little bit more time to think? Should we go through it together? Okay. Does anyone have any ideas that they would like to share? On how we could start approaching this? Yeah?
We could assume two solutions and then assign them to variables so we could work with them.
Great idea, right? Basically, what do we know? We know that there are more than two solutions, at least two solutions. So let's write that out mathematically, right? Like assume that there are two solutions that are distinct and see what we can do to work with that. So let's try that idea. So again, we have basically the beginning part, which is this if part. This if and then this then is basically an implies, and this is the second part of our statement, right? Okay, so in our proof, we're going to say, okay, let's first write out what we know. We say that ax equal to b has two or more solutions. So, okay, let's say we have two or more solutions. So say let x1 and x2 be two distinct solutions. Right? This means that x1 is not equal to x2. Right? We can't just say, oh, here's a solution. Oh, here's a solution with the same solution with a different name. That's not two solutions. That's one solution with two names. So x1 and x2 are two distinct solutions. What does it mean to be a solution? It means that a times x1 is equal to the vector b, and a times x2 is equal to the vector b, right? What do we want to show? What is the end part, right? So this is the statement that I underlined in pink. What do we want to show, right? We should always keep in mind, like, this is what we know, this is what we can assume, where do we want to go? Well, we want to show that the columns are linearly dependent. And what does that mean? From our definition, we know that basically we want one column to be written as a linear combination of the other columns, right? So we want for some ai, the column ai is this linear combination, right? J is equal to 1 to n, j not equal to I, cj, aj. Right? We want to find some I for which this is true. Okay? So here, what do we have? We have a times x1 equal to b1. What is a times x1 in terms of the columns of A? Remember, you want to get somewhere which has the columns of A, right? So we want to start thinking about what we know in terms also of the columns of A. So ax1 is essentially a linear combination of the columns of A, right? So it's not exactly what we want, but it's something similar. And we have ax2, which is another linear combination of the columns of A. So what if we were to combine them? What if I was to say, well, it turns out that a times x1 is equal to b, and a times x2 is also equal to b. What do you want to write? What do you feel like writing, given that you have these two nice things that are equal to the same thing? They're equal to each other, right? So we can write ax1. This implies that ax1 is equal to ax2, right? I can further rewrite this as a times x1 minus x2 is equal to 0. I just moved one thing to the other side, right? So we now have a linear combination of the columns of A is not equal to another column, but it is equal to 0. Right? So now you have some equation where all of the columns are on one side and there's 0 on the other side. But what you want is you want one column on one side and all of the other columns on the other side. So you want to pull out one column, right? So the question is, how do you do that? So for that, let us say, let's give this vector a name. Let y is equal to x1 minus x2. Okay? So we can now write A times y1, y2, yn is equal to 0. If y has these elements, y1, y2, yn, right? Can you further now, how can you write this into something that looks kind of like this? Yeah? Great, right? You want to move to the column vector, so the idea is express A as the column vectors. So let's write this as y1 times a1 plus y2 times a2 plus dot dot yn times an equal to 0. You know, where A is basically the matrix A1, A2, AN. These are the columns of A. Now what do you want to do? Can you use this to get something like this? How would you want to do that? The suggestion is to leave A1 here and take the others to the other side. Right? That's a good suggestion. What do we have to check to be able to do that? So let's do that. We will take A1 to the other side, but we have to check one thing, right? Do we want AI times some constant CI here? No, right? Our definition says it has to be a 1 here. So what do we need to make sure that we can do? Something can't be 0, right? I'm hearing all these murmurs. I need to be able to divide somehow. Well, so to be able to divide, I need to make sure that, let's say I want to divide. I need to make sure that y1 isn't 0. Is everyone following me? Yeah? Okay. So do I know that y1 isn't 0? What if the first component of x1 was equal to the first component of x2? y1 would be 0, right? So can you move a1 over? What about a2? Can you guarantee that y2 is not 0? So what do we do now? Yeah, at the back? Great idea, right? What he's pointing out is that, wait, we know that x1 minus x2 is not equal to 0 because these are distinct, right? So, is it possible for every single entry in this vector to be 0? There must be at least one entry that is non-zero. Do we care which entry it is? No. So we can say, without loss of generality, let y1 not be equal to 0. You could also say, without loss of generality, let y13 not be equal to 0. That is valid, but you have to write more stuff because there's 2 digits in 13. I recommend choosing a small number. So we say, without loss of generality, let y1 not equal to 0. Now I can say a1 is equal to negative y2 over y1, a2, plus negative yn over y1, an. And basically, we're done, right? We have exactly what we wanted. So, QED. We have proved our theorem. Any questions on what just happened? Yes? Yeah, good question. How did I get the last equation? I basically said, let's take y2 to yn over to the right-hand side. And then so I got a negative sign because I did that. And then I divided by y1. Yeah, question. What would happen if you had more than two distinct solutions? Great question. The same proof would still hold, right? Like, we don't use the fact that there's more than two distinct solutions. Yeah?
What if it's just talking about everything in terms of like and you do what you did with like that earlier proof from yesterday where it's like you assume A has 6 columns and then you assume that like Y is
Good question. The question was, why did you here not do the same thing you did last time, which is, last time what we did was we said, let's pretend that, where did it go? We did this small case first, right? We did this simple example first. But this simple example doesn't imply the proof for n. We just did this as a way of understanding how the proof works. And then we made a separate argument for the case when we actually had n columns. But in this case, we were able to, skip doing the simple example. That doesn't mean that you shouldn't do the simple example. If you're stuck on how to get started, definitely use the simple example. There, because that proof was slightly more complicated. So starting with a simple example made it easier to see the pattern. So you don't always have to do a simple example first. That is primarily a technique for understanding. Yeah, good question. Other questions? Anyone? Yes, green shirt. QED means that was to be shown. Latin for that was to be shown.
we use the other definition of linear dependence?
We'll get to that.
Right now you only shown this for two unique solutions. I mean, how does that extrapolate to multiple unique solutions?
Great. So good question. What about multiple unique solutions? I think that was also a question at the back. What if someone told you that you don't have two unique solutions, you have like 53 unique solutions? This proof would still exactly hold because you could just choose solution 1 and solution 2 and still go through the whole argument. So you still know as long as you have 2, you have linearly dependent columns. If you have 53, you definitely have linearly dependent columns because you have 2. Yeah. Okay. So this leads to us thinking, well, can we have a different way of thinking about linear dependence? And I want to actually introduce the second definition of linear dependence. It's not really important which one you use, but it's good to know both of them. Because basically what you see is that you can either have one column be a linear combination of the other columns, or you could have a linear combination of all of the columns be equal to 0. What you just argued here is that these two are the same, as long as not all of the coefficients here are 0. So there's a second definition. Thank you. for linear dependence, where we say A1, A2, AN are linearly dependent if there exist C1, C2, Cn not all 0 such that C1, A1 plus C2, A2 plus Cn, An equal to 0. And you should go and convince yourself, if you're not already convinced, by using the argument we followed here, that this definition is exactly equivalent to the other definition. This is another good thing to practice as a proof. Worth doing on your own. Okay, so I just wanted to introduce that, and basically you see, through this proof, why it's natural in some cases to want to use this definition. So if we had known this definition in advance, and if we had known these were equivalent, we could have stopped our proof right here, after we had argued that one of the elements of the vector y was non-zero, because that gives us exactly this. Okay. So I want to now move to a kind of new topic. And I want to start talking about linear transformations. Which is really, the understanding of linear transformations is why we want to study linear algebra, because matrices effectively represent linear transformations. And in fact, they are linear operators. So yesterday in discussion, you saw an example with the following matrix, right? You saw cos theta minus sine theta, cos theta, right? You saw this matrix. Let's call this matrix A. And what did this matrix do? Let's say this matrix A operated on this vector, 1, 0. What do you get out? You get out, basically, cosine theta, sine theta. So if I was to draw a picture, I have my vector here that is 1, 0. I have another vector here, cos theta, sine theta. Right, and multiplication by this matrix transformed the 1, 0 vector into the cosine theta, sine theta vector, right? It rotated by this angle theta. And you saw in discussion why this is a rotation matrix. Right? You argued that no matter what vector you have, not just for the 1, 0 vector, but for any vector, you will actually rotate the vector by an angle theta when you multiply by this matrix, right? Everyone, does that sound familiar from discussion? Yeah? Thumbs up? Yeah? Okay, good. People saw this. Good. Okay. So this is basically what is the essence of a transformation, right? It's taking a vector, transforming it into something else. What about the following matrix? This is also a transformation. What transformation is this? Can you figure it out? It's a reflection. Why is it a reflection? Let's say I multiply the vector xy by this. what do I get out? I get x remains unchanged, but what happens to y? Negative y. Is everyone with me also in the back? Yeah? Okay. So this is a reflection matrix. It's another kind of transformation. What about, this matrix? I don't know, 13, 53, since those are the numbers of the day, 2 and 5. This is another matrix. When I multiply a vector by it, what happens? I get some other vector out. It doesn't have a nice name. It doesn't called rotation or reflection or something like that. But it is also a transformation. And the next couple of lectures are going to build exactly on this understanding of transformations. So a matrix is a linear transformation. And we say that a function, or f is, an operator f is a linear transformation. If f of x plus y is equal to f of x plus f of y, and f of alpha times x is equal to alpha times f of x, where alpha is some constant. The first thing is often called as preserving addition, and this is called preserving scalar multiplication. Don't worry about the terminology. You don't have to know that. You just need to know the math. So don't worry if the jargon is not your favorite thing. And we know that this is true for matrices, right? If I have a matrix A, I know that A times x plus y is equal to A times x plus A times y. You saw that it is distributive in discussion last time. And if I have A times alpha x, this is equal to alpha times AX. Right? So you know this about matrices. What's an even simpler example? What if I had f of x is equal to, let's say, a vector x, 2x? Right? If I take f of x plus y, this is basically equal to 2 times x plus y, which is equal to 2x plus 2y, which is equal to f of x plus f of y. It's important to note how all of these steps happen, right? They're super easy. But here I'm saying f of this argument, f of x plus y, means I take whatever is in the brackets and multiply the whole thing by 2. And f of x means I take f of this argument and multiply it by 2. So no matter which way I do it, I get the same result. So this is linear. What if I have to check the other thing, which is f of alpha times x is equal to 2 times alpha times x is equal to alpha times f of x. Also good. What's an example of a transformation that isn't linear? If I take g of x is equal to x squared, then you can see that, let's just take this as a scalar, f of x is equal to, let's say f of x plus y is equal to x plus y whole squared, which is equal to x squared plus 2xy plus y squared, whereas f of x plus f of y is equal to x squared plus y squared. Right, so this is not linear. This is linear. Okay? Everyone understand this? Okay, good. Just some terminology that you should know about. Okay. So I want to now move to talking about even more general transformations. And one of the powers of linear algebra is that matrices and vectors can be used to represent lots of different kind of systems. And in fact, vectors are often used to represent the state of a system. So you have a problem on your homework this week about modeling a car and modeling the trajectory of a car, right? And one of the first parts of the problem says, express this system in matrix vector form, where the state of the system is basically properties of the vehicle, right? So for example, let's say you have a vector that denotes the state of a car. Well, if x of t is my x coordinate of the system at time t, y of t is my y coordinate of the system at time t, and let's say v of t is my velocity at time t, right? I have some car, it's going in some trajectory, here's my axes, this is, let's say, the trajectory of my car. Then I can represent this by this vector, x of t, this state, y of t, and v of t, as the state vector at time t. You can call it, let's say, maybe this is some vector s of t. And why do I have this of t here? I'm saying that, well, the car is here at time 1, here at time 2, here at time 3, here at time 4, here at time 5. I'm tracking it as it goes along in time. It's a state because it's evolving. So you see a little version of this in the homework this week. And if you get more interested in basically the field of control, which uses this kind of modeling very, very heavily, then 16B will go into much more details on how this kind of modeling can be used. And your final project will rely heavily on this kind of modeling. And then if you get interested in this kind of stuff, you can go on to take classes like 106 and 128 that will go into a lot more details on how you can use linear algebraic tools to figure out how to, let's say, drive your autonomous car. But I want to use this just as an example, and we don't quite have the tools to talk about state transformations in the case of autonomous driving yet. But I want to talk about state in a simpler system. And I want to talk about the following simpler system, which is a system of pumps and reservoirs. So I want to figure out how a system is evolving in time, and I have the following system. I have 3 tanks. I'm going to call them A, B, and C. These are tanks of water. And they're all interconnected, and water flows from one tank to another. So this might be modeling, let's say, the water storage system in the city. These kind of models will also show up when you're thinking about smart grids. So basically, you can think of these each tank as modeling a storage of energy, but sometimes you need to transfer energy from one location to another. You will see even more generalized versions of the model that we're going to talk about when you take classes like CS70 and 126. And these tools will help you for the models that you will be learning there. So what we want to do with these tanks is we want to understand how water is flowing in them. So let's say I have tank A, and I have a pump, and every time the pump runs, water is transferred from one tank to another. So let's say I represent the water in my tanks by state. So I have XA of T, which is the water in tank A at time T, and XB of T and XC of T, which are the same. Okay? And now I run my pumps. And every time I run my pump, let's say all of the water in B gets transferred to C. There's a pipeline, everything is instantaneously transferred. And all of the water, so fraction 1, and all of the water in C gets transferred over to B. And let's say the pump A doesn't want to interact with anyone. A is just pumping to itself. So I'll draw it by a self loop. Every time the pump runs, A takes all the water in itself, puts it back in itself. So now, how can I figure out what is going to happen to the system as it's evolving? Let's say I call this vector. I stack these, and I call this a vector, x of time t. What is x of t plus 1 in terms of x of t? How can I figure this out? Well, I can write this as a system of equations, right? How can I write this as a system of equations? Take a minute and maybe try to write out a simple system of equations between xa of t, xb of t, xc of t on one hand, and xa of t plus 1, xb of t plus 1, and xc of t plus 1 on the other. Assuming that you know exactly how these pumps are flowing. This is the structure that you have set up. If you have a question and the setup is unclear, feel free to ask as well. Yeah. What's the arrow mean? This thing? So all the water from B goes to C, and all the water from C goes to A. That's what this means. And this arrow means that all the water from A goes back to A. Does that clarify it? The one means fraction 1, so 100%. So if I was to write half, it would mean half the water from A would go to B. Good question, yes. Yeah? You don't even have to think about it as a matrix yet. Just write a system of equations. Okay, so let's think about it together, right? What is the system of equations? What do we know about the first pump? We know that when the pump runs, all the water from A goes back to A. So is there any way for the water in A to change over time? No. So we have XA at time t is exactly equal to XA at time t plus 1, because there's no change allowed. What about XB at time t? Whatever is in B at time t, it goes to C at time t plus 1, right? So this is equal to XC at time t plus 1. And finally, we have XC at time t is equal to XB at time t plus 1. This is the relationship, right? So now, if I want to write, let's say, XA of t plus 1, XB of t plus 1, XC of t plus 1. In terms of the vector, XA of t, XB of t, XC of t, well, I have basically linear equations, right? I can write this as a matrix. And I want to figure out basically what is called the state transition matrix for this system. Because what this is saying is that it's telling you every time the system evolves, every time your clock ticks and your pumps run, how does your current state vector go to the state vector at the next time? So I know that XA at t plus 1 is just equal to XA at t. So the first row, what am I going to write? I'm going to write a 1, 0, 0. XB at time t plus 1 is exactly what XC is at time t. So this is going to be a 0, 0, 1. And finally, XC is given by XB. So I have a 0, 1, 0. This guy is called the state transition matrix. Does everyone understand what we did here? We just took these equations and wrote them into matrix form. Okay. So now we know that, let's say at time 1, we had some water in our tanks, right? Let's say we had, at time 1, XA of 1, or let's just call it the vector X of time 1. Thank you. Vector X at time 1 is equal to, let's say, 1, 2, 3. Right? There's 1 unit of water in tank A, 2 units in tank B, and 3 units in tank C. What's going to happen at the next time step? This is going to remain the same, but these two are switching, right? We're going to keep having this flip-flop, flip-flop, flip-flop happen as the time goes on. So this is a particularly easy setup, and we can understand just by logic how these quantities are going to move. But what if in general we wanted to write x of t plus 2 in terms of x of t? Or x of, t plus 2000? Can we figure out how this system will evolve over time as time gets larger and larger just by understanding the state transition matrix? That's the question that we want to ask. Because, for example, this is an example that we're thinking about in the case of pumps, but if you're thinking about this for energy, you want to understand, if you keep transferring energy in a certain way, where is your system going to end up after you keep running this for a long time? Or if your state vector is modeling your self-driving car, then you want to know if I keep, having transitions according to the state transition matrix, where am I going to end up? So I'm going to call this matrix over here, this matrix Q. And now I know that q times x of t is equal to x of t plus 1. Q times x of t plus 1 is equal to x of t plus 2. Right? So what is x of t plus 2 in terms of x of t? I can just substitute, and here I get q times x of t. And so what I really want to understand now is this q times q. What does this even mean? This q operator is happening twice. And we know in this case that when q happens twice, what do you get back? The original configuration, right? So we know intuitively that's what's going to happen, but let's try and see what happens in more general cases. And for this, I want to define now. Let's see. Put this here. Okay, you can kind of see this. Matrix. I want to basically define what happens when I, take this matrix Q and apply another matrix on top of it and another matrix on top of it. What happens when I keep compounding transformations? Here it so happens that we started out with an example where I keep running the same pump over and over and over again. But maybe I run different pumps at different times, right? So I want to, in general, understand what does it mean to have matrix A times matrix B. And let's think about it in, again, the simple 2 by 2 case. So I have A11, A12, A21, A22, and I have B11, B12, B21, B22. And it turns out that matrix-matrix multiplication is really no different than stacked matrix vector multiplication. So if I look at this matrix B here, I can think of it in terms of its columns, right? And so, when I want to multiply a matrix A and a matrix B, it's like basically doing A times the first column of B, and then stacking A times the second column of B, and then stacking A times the third column of B, so on and so forth. So if this is column vector B1, this is column vector B2, this is basically the same as this matrix A times B1, B2, which is equal to matrix A times B1. What shape is A times B1 going to be? It's also going to be a column vector, right? And then stack next to it A times B2. So to do this out, I know how to do matrix vector multiplication, so I ignore this, and I say, well, A11, this row is going to multiply this column. So A11, B11, plus A12, B21 is going to be the first element. So this is going to give me A11, B11, plus A12, B21. And then here, I'm going to have the second row times the first column. A21, B11, plus A22, B22. So this is the first, this is basically saying what happens to B1. Right? This column is A, B1. Now we have to write A, B2. And so here I'm going to now ignore this guy, and just say A11, B12 plus A12, B22, and then A21, B12 plus A22, B22. And this line you would not usually draw. I'm just drawing it here for your reference. Question? It should be this row times this column. So A21 times B11, A22 times B21. Yes, thank you. So there's nothing that we did differently other than what we would do for matrix vector multiplication. In general, if I have A times B and they're not two-dimensional, how would I write this? This is just A times B1, B2, Bn, which is equal to AB1, AB2, ABN. I just have a stack of vectors, and I treat matrix multiplication as just doing a bunch of matrix vector multiplications one by one. Any questions on this? We're good? Okay. So now we can move on to doing the interesting stuff, right? We wanted to say, going back here, what happens when you have this Q times Q, right? There's no way you can see all of three of these things at the same time. Okay, which page do you want to see? This page or this page? In my right hand or left hand? Okay. I'll just go by chronology. I'll rewrite this Q. The Q, the transition matrix we had earlier, was the following. We had Q equal to 1, 0, 0, 0, 0, 1, 0, 1, 0. Right? And we wanted to figure out Q times Q. So let's do it. So if I had Q times Q, this is equal to 1, 0, 0, 0, 0, 1, 0, 1, 0. I'm going to treat the second Q as 3 columns. And here I'm going to take this perspective. This has the 3 rows. So let me do Q times the first column, right? So if I do Q times the first column, I have 1, 0, 0 times 1, 0, 0. So I get a 1 here. 0, 0, 1. This 0 goes to this 0 maps to this 0 goes to here. So I get a 0 in total. And this 0 times this element plus 1 times 0 plus 0 times 0 gives me a 0 here. Take a minute and do the other 2 columns yourself, because it's hard to follow when someone else is doing them along. But just take a minute to do the other 2 out yourself and ask me if you have a question. So what would you get in this position? Now we're just thinking about the second column here. So it's the first row of Q times the second column is what you would get here, which is, I'm worried that I've lost some people. Okay, questions? So here, I'm basically going to have this element times this this element times this, and this element times this, right? It's just matrix vector multiplication doing it again. The second point here, now in the second element, I have the second row times the second column. In the second row and the second column, the ones line up, right? Which is why I get a 1 here. And the third row and the second column, they don't line up, so I get a 0 here. And similarly here, I get a 0, 0, 1. What is this matrix? It's an identity matrix, right? It's a familiar thing. What did we expect to have happened when the pumps ran twice? It's the same thing. So the matrix multiplication is doing the right thing. It's matching our intuition, right? It's giving us back the identity transformation or the identity matrix. So this was a simple example. I want to give you a chance to do a slightly more involved example. So let's look at this other example. Let's look at A, B, C. And A is now such that it only keeps 1/3 of its water for itself, but it sends the other third to B, and it sends a third to C. What does B do? B keeps half of its water for itself, and it sends half of its water to C. And C keeps 1/4 of its water for itself, and sends 3/4 to B. So why don't you try to write the state transition matrix for this pump now? We want to have x of t plus 1 is equal to sum q times x of t. What is q? Feel free to discuss it with each other. You don't have to do it alone. Let's see what this looks like from the back in the meanwhile. Okay, it's actually legible. So how many people think they have the transition matrix? Yeah? Okay. How many people want another minute? Okay, 1 more minute. Okay, let's do it together now. So, what do we know about the water from A? Water from A is going to itself, and then it's going to the two others, right? The water from B is going half to itself and half to C. So B is not giving anything to A. And C is not giving anything to A either, right? A quarter of it is staying with C, and half is going to B. So let's be very careful, since we haven't done this a lot, and write this out, as a full system. So XA of t plus 1. So what is A receiving water from at the next time step? A, right? And how much? It's a third of the water in the previous time, plus 0 times what it's getting from B, and 0 times what XC has. Okay? What about XB of t plus 1? Well, is it getting any water from A? A third, right? 1/3 XA of t plus it's getting half of what was in B, plus it's getting 3/4 of what was in C. And XC of t is going to be, it's getting a third of the water in XA, plus it's getting half of the water in B, plus it's getting 1/4 of the water that it itself previously had. And now we can write this in this format, where now this Q, the first column is just 1/3, 1/3, 1/3, 0, 1/2, 1/2, just reading off column by column, 0, 3/4, 1/4. Right? So if you get confused about how to go from a graph to a state transition matrix, you don't need to be able to just jump directly. When you're first doing this, just write out the equations, right? And then you can just read it off. It's much easier. Okay, so basically the columns here are representing the outflows, right? The first column is the outflow from A, right? The second column is the outflow from B. The third column is the outflow from C. And if you look at the rows, these rows are the inflows. A is getting nothing from anyone other than itself, right? That's what this row is telling you. So now, intuitively, every time the amount of water in A is going down by a third, right? So if you keep doing this, at the end of time, how much water is going to be in A? 0, right? There's smaller and smaller and smaller fraction going to be in A. So this is what we feel intuitively. But if we wanted to really understand this, if we wanted to mathematically say this, and if we wanted to, importantly, figure out, well, how much water is going to be in B? How much water is going to be in C? What we would want to understand is basically Q times Q times Q times Q, right? For many, 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 many time steps. Because that is what you'll get. And I don't want to do that multiplication out, so I'm going to do it here. So what I did, can people read this at the back? Are the numbers visible? Yeah? Okay. So here I just wrote this matrix Q out, right? And this Q is exactly equal to the Q we had over there. And then I said, well, let's take Q1, which is Q times Q. And this is what we're going to get when the pumps run once. and you'll see that, well, there's going to be less water in A, but it's not all the way gone to 0 yet. Now Q2 is Q1. Q1 was already Q squared. Q squared times Q. So now I get the next matrix, and the next matrix. And now Q3 is Q2 times Q, right? I keep adding one multiplication by Q. That's a lot of work. So then I said, well, what if I just, Python has nicely implemented functions for me, and I can just say, well, what if I take the matrix to the power 20, multiply it 20 times? What do you see here? This is basically the amount of water that's going to be in A, and it's essentially going to 0. Whereas the water in B is basically B and C are basically sharing the water in a 60-40 proportion. So go try this out on your own, and you'll see basically how these different, things are evolving, and how matrix multiplication can help you understand how systems are evolving in a longer term. So finally, before we finish, I wanted to introduce one more thing in the last few minutes, is 2 properties of matrix multiplication. First property is that matrix multiplication does not commute. What this means is that the order matters. The order in which you transform things is important. You cannot run a pump 1 and then pump 2, or pump 2 and then pump 1. Right? Because think about it. Let's say the first pump you ran emptied all of the water in tank A, and the second pump says give half of A to B. Right? In that case, B is going to get nothing. But on the other hand, let's say you ran the second pump first, then half of the water is going to go, and then half of the water is going to get emptied, right? So matrix multiplication does not commute. A times B does not in general equal to B times A. There are some exceptions when this is true. This is not always the case. So as an example, if you take, for example, what's a good example? Let me do the example I did. 0, 1, 1, 1, 2, 3, 4, versus 1, 2, 3, 4, and 1, 0, 1, 1. Right, what is this equal to? This is basically going to give me 1 and 4, and 2 and 6. And here I'm going to get 3 and 7, and then 2 and 4. Right? It's worth checking this, verifying for a few examples that, if I change the order, stuff does not stay the same. This is important property 1. Important property 2 is that matrix multiplication is associative. So what this means is that if I take some vector x, and first I transform it by the matrix A, then by the matrix B, then by the matrix C, I can do this like this. Or I can say, well, I'm going to first compose these 2 transformations and then apply them directly on AX. So CBA is equal to C times B times A, which is equal to C times BA. It doesn't matter which ones you do first. It doesn't mean you can change the order around. Note that this is not equal to ABC, right? But as long as I don't change what is next to each other, I can still go ahead and do the operations in any which way I want. So I'm going to end there and see you next week. if you had good question. So
like a 1 by 3, I guess.
yeah. So if you had a 2 by 2 and a 1 by 3, that doesn't work.
Okay.
A 2 by 2 and a 2 by 3 will work. Basically, the number of columns in the first matrix has to equal to the number of rows in the second matrix.
Okay, so you can't have like more rows in the second matrix or first matrix than the
No.
other.
So you can have. So for example, here you could do like 1, 0, 1, 1, and here I can add as many columns as I want, right? Remember, A times B, like if I show you the picture. Thank you so much.
Yeah, of course. He emailed Ezra, so he should hopefully
Okay,
figure
great.
something out.
Thank you so much.
Yeah, of course.
So here, the rows, the number of columns here, or the length of the row, has to be equal to the number of rows here. So number of columns equal to number of rows. So
Okay.
if this is, if A times B, if A is M by N, B can be N by R. But these two have to match. Because you
Okay.
can see, like, I can keep adding any number of columns, and that's totally fine. But I cannot add rows to B.
Okay.
Right? So M is the number of rows of A, N is the number of columns. So the number of columns of A has to equal to the number of rows of B.
Okay.
Yeah,
Okay,
good question.
cool. Thank you.
Yeah.
I understood the water tank example